So my name is Sachin Verma, and I'm currently a PhD student at Department of Physics, IIT Roorkee, and I'm currently working under the supervision of this Professor Ajay. And currently, I am working on the thermoelectric transport properties of these strongly correlated quantum dot-based hybrid devices. And here I'm going to briefly present my research work, which I did in last like 3 or 4 years. And I want to thanks Chris for giving me this opportunity to present my work. Okay, so let me first briefly highlight our research interest and recent publications. So, I theoretically study the spectral and transport properties of this hybrid superconductor and normal metal or quantum dot based devices. So, in these devices, the electronic correlation or many body effect plays a dominant role, and we have to use the tool of many body green function theory or quantum field theory to understand these hybrid nanostructures. So what we did is that we solved the Hamiltonian returning the second quantization formalism by various analytical techniques such as green function equation of motion, perturbation theory, and non-perturbative techniques like slave boson. And for numerical computation, we use Fortran coding language or MATLAB software. So these are our recent publication. Uh, Sorry. So this is our recent publications. So we have published two papers in Journal of Physics Condensed Matter, and recently we have submitted one manuscript in European Physical Journal B. And here I'm going to briefly highlight this first two one. Okay. Okay. So let me first briefly show you some experimental devices which have been fabricated very recently by various experimentalists across the globe. So it ranges from this single quantum dot rate particle heat engine to this more complex device. The first one is the single quantum dot based heat engine, which have been fabricated very recently by Josephson and his group. And we theoretically reproduce the experimental result, and then we extend this study for a superconductor based device. And the second one is this NQDS based device, and the third one is this quantum dot based Josephson junction. So instead of insulating layer between these two superconductors, there is a quantum dot, so we can tune the properties of this uh, device. And third one is more complex quantum dot based heat wall. So our interest lies in these three devices. So these are the recent reviews. So uh, let me first show you this single electron based or single quantum dot based heat engine. So here, this group Josephson recently fabricated this device experimentally. So what happened is that when there is a thermal biasing between these two normal reservoirs, then due to this temperature difference, electron flows from the left to right electrodes, which creates a, you can say, potential difference. It generates a thermovoltage due to this Seebeck effect, and that voltage can be uh, used in this external serial load resistance R. So there is two pair. This second one is this schematic diagram for this experimentally fabricated device. So there are two conditions. The first one is that when there is no load resistance in the external circuit. So when there is a, so we have to apply an external voltage to counterbalance these thermally induced electrons. So there is a generation of power output, which means this voltage V is equal to zero and V is equal to infinite, and the maximum power output is lies when this thermal voltage is VTH by 2, and then there is a external load resistance in the circuit. Then we have to like optimize it to find out uh, the maximum power output. Okay, so theoretically we started from this something called single impurity Anderson model in second quantization formalism or occupation number representation. So here I've shown the Hamiltonian returning second quantization formula, that is in terms of this radiation and annihilation operator. So these are quantum field operator, which was initially used in in particle physics in quantum field theory, and then people have used it in condensed matter physics, and it can be used to study these strongly correlated systems. So this first term represents the uh, Hamiltonian of this normal non-interacting reservoir, and the second term represents the quantum dot. So in the second term, the first term E d plus d sigma dagger d sigma is this kinetic energy of electron on the quantum dot level, and the second term is the on-site Coulomb repulsion, and the third term is the tunneling between this metallic reservoir and quantum dot. So this Hamiltonian has been widely used to study this uh, uh, charge transport properties in Coulomb blockade and contour regime. And the fully analytical solution is only possible when this U part is zero. And when U is zero, then problem is exactly solvable. However, in real systems, this U is the important parameter. So we need to apply various approximations such as Hartree-Fock mean field, Hubbard one or beyond that. And we have considered that finite U. And we also assume that the quantum confinement effect dominates over the thermal energy, such that the energy separation between these two quantum dot uh, level is much, much greater than the thermal energy. So we restrict ourselves to the single quantum dot, single energy level quantum dot. Okay. So to calculate the thermal transport properties or charge transport properties or spectral properties, uh, we uh, need to have a basic idea about this something called the propagators or green function or correlation functions. So this something called this retardant gain function provides the information about the spectral properties or density of state or scattering rates of these devices, and this lesser and greater gain function is directly linked to this observables such as kinetic energy or kinetic properties or like density of state or currents. So we have calculated this green function using various approximations. So here I have shown the green function, uh, which we have calculated for our normal metal quantum dot normal metal systems by using this Hubbard one approximation. So we calculate this green function, these various elements of this green function, where this first element is the green function of the electron with the spin up, and this 2 element is the green function of the hole with the spin down, while these off diagonal terms are only non-zero in case of a superconductor. And then we use this Keldyar's green function equation to calculate the lesser green function, which is used to calculate the non-equilibrium properties, such as the occupancy of the quantum dot. And the occupancy need to be calculated self-consistently because this occupancy also depend on this green function. So we have to calculate this self-consistently. So we did it using the Fortran coding language or MATLAB. Okay, can you hear me? Hello?
Yes, of course. Please go ahead.
Am I okay? Okay. Okay. So let me now give you a brief theoretical description of this systems. So now the green function, as I told before, that for a finite on dot Coulomb repulsion, one need to apply these approximations such as Hartree-Fock mean field, Hubbard one, or beyond that. So we have used this something called the equation of motion technique, where we write down the green function in terms of this Jubrev notation, and then we apply this approximation to end this hierarchy of these equations. So the first one, the simplest one is this something called the mean field approximation or Hartree-Fock mean field approximation. So we directly like uh, take this occupancy out, and the green function the equation reduces to something like this, and then we neglect these higher order correlation functions. So this the simplest one is this Hartree-Fock mean field approximation. And then if the Coulomb repulsion is moderate or large, then we need to go beyond that. So the next one is in the next one, in the higher order approximation, one need to write down the equation of motion of this kind of green function. So we use then the Hubbard one approximation, and to capture the qualitatively the Kondo effect, or to capture the very strong Coulomb repulsion, one need to go beyond this Hubbard one approximation, and which is known as this Lacroix approximation. So we have also used this Lacroix approximation. So this Lacroix approximation qualitatively captures the Kondo effect and also correctly explains this Coulomb blockade effect. So here we have compared this mean field, Hartree-Fock mean field and Hubbard one approximation for these NQDN systems. So here we have plotted this electrical conductance, thermal conductance, thermopower, and figure of merit for NQDS system using Hubbard one and Hartree-Fock mean field approximation. So the blue one shows the mean field decoupling, while the red one shows the Hubbard one decoupling, which is more better as compared to. So here it is clearly seen that uh, this Hartree-Fock approximation completely fails. So it just captures the very broad features, doesn't like captures the sharp features in these properties. So the conclusion is that one can't apply this Hartree-Fock mean field approximation in non-equilibrium situation. One need to go beyond that. So we have considered this Hubbard one approximation as the our initial point. Okay. Now, once the green
By the way, we have a lot of time, so don't rush. Don't rush. Take your
okay,
time.
okay, okay. So once this green function is known, then we can calculate the current or heat current or power output or this efficiency. So for that we have used something called Kildias formalism. Or the current is given as the time rate of change of this occupation number on the quantum dot, which we can simplify using this Heisenberg equation, and we can simplify it in this form, which is known as sometimes known as Landau-Buteyko formalism or Mayer-Windkind formalism. So the first term, this one is the current, charge current, and similarly the heat current can be calculated, where this T omega is the tunneling amplitude, which is nothing but this model square of the Italian Green function. And then we can also calculate other thermoelectric quantities such as thermovoltage, thermopower, and thermal conductance, and thermoelectric efficiency by using this relations, which is given here. Okay. So now in the linear response regime, the Fermi distribution function can be simplified by using this Taylor series expansion. And now we can substitute this into these equations, and then current and this charge current and heat current reduces in a much simpler form in a linear response regime. And then we can calculate the power output. There are two situations. The first one is that when there is this open circuit condition, when the external load resistance is infinite. So we have to like solve this equation, which is I, which is a function of thermal voltage and temperature difference is equal to zero. So we have to solve this equation to find out this thermal voltage, and this is the one case. And in another case, we have a finite load resistance in the external circuit, then the equation becomes slightly different, which I will explain later. So power, as I explained previously, a power is generated between V is equal to 0 and V is equal to VT, TH, and one can find the optimal power output. So for detailed theoretical formalism, one can check this book and also recent publications. Okay, so let me now come to the results. So this first one is this Hubbard one results, which we have applied for N2DN system when both the source and drain are normal metallic and a quantum dot is attached to them. So these are like non-linear transport properties. So the first one, this first three graph, this is the thermo uh, power. Then this middle one is this thermal conductance, and the last one is this figure of merit or efficiency, thermoelectric efficiency. So now one thing which is clear from this plot is that both this thermopower and thermoelectric efficiency, this becomes zero at the particle hole symmetric point and at the resonance point. So whenever there is a matching of this energy quantum dot energy level and reservoir energy levels, then electron and hole they compensate each other, and this thermopower and as well as this thermoelectric efficiency, they it goes to zero. So however, when ED is like above and below these points, then the uh, the thermopower due to electrons is a bit higher as compared to holes, and it gives us the positive value. It gives us this negative values, this blue one. And on the other hand, in case of thermal conductance, it adds up at the particular symmetric point due to hole and electrons. So they adds up and gives us this sharp peak at this particular symmetric point. However, uh, this large uh, this large thermopower and figure of merit or thermoelectric efficiency is only visible when this thermal gradient uh, or temperature difference between these reservoirs is small. As we increase the temperature difference, the Coulomb repulsion is reduced, which further reduces these properties. So we have recently submitted this manuscript in European Physical Journal B. Now, Now, okay. So now, in order to explain the experimental results, one need to go beyond this Hubbard one approximation because in experimental device, the parameters are this. So one can see that this U or Coulomb repulsion is the largest energy parameter as compared to other relevant energy parameters. So one need to require this infinite U technique such as slave boson or Hubbard one mean field approximation or beyond Hubbard one approximation. So we have applied this Hubbard one or beyond Hubbard one approximation and calculated these green functions. And then we consider u is equal to infinite limit in this approximation that in this green function, and the it reduces to a much simpler form where this E0 and E1 self energies are given by these expressions. So now let us plot this u is equal to infinite results, and what we find is that uh, beyond Hubbard one or in U infinite limit, the thermal quantities uh, shows a similar behavior as for non-interacting case. However, there is a difference between this non-interacting and interacting case, and that is that two peaks have different magnitudes, which one can see, and it is due to different degeneration of electrons. So whenever there is an even number of electron on the quantum dot, then it becomes easy for another electron to jump back to that electron. So whenever there is an odd number of electrons, so that odd electrons repel another electrons, and it creates a smaller power output or smaller thermal conductance. So the maximum power output and the efficiency also one can see that it can enhance from like a factor of 100 times, and the efficiency can enhance by a factor of 20% when kBT is increased from this 0.01 to 0.5, which is this correspond to a temperature of 0.1 Kelvin to 5.8 Kelvin. And also one can clearly see the violation of Weidmann-French law. So this large thermoelectric figure of merit or efficiency is due to this violation of Weidmann-French law. The quantum dot based systems violates this Weidmann-French law. Okay, now let us compare the results with the experimental results. So now, as we have, uh, as I told you previously, that in case of a finite load resistance in external circuit, the condition becomes something like this. So which is simply not something like this. It's just Ohm's law. So we have to solve this equation to calculate this thermo voltage and then the power output and the efficiency. So we have calculated this maximum power output and corresponding thermoelectric efficiency as a function of this as a function of this load resistance. So we have first optimized it with respect to the gate voltage, that is quantum dot energy level, and then we have optimized it with respect to this load resistance. And it is seen that the our theoretical results is like exactly as it was seen in the experimental study. So it reproduces the u is equal to infinite limit, reproduces this experimental results quite well. And this one can say that this infinite u provides a more practical limit to study these NQDS systems. And we have submitted this paper recently. Okay, now the experimental limit or the experimental range is like very limited when this gamma is small. So this inset here shows the experimental limit. So this small like arrows, double arrow, it shows the value of gamma by KBT, which is considered in experimental study. However, we extended this uh, maximum power output and efficiency to the other parameter regimes, and it has been found that for even for large gamma by KBT, which was like consider that at large gamma by kBt, the power output or efficiency is very small. But we have found that if we choose this external load resistance correctly, then one can have a finite power output and finite efficiency even at large gamma by kBt. So it is due to this something called the maximum power transfer theorem. So when we increase gamma by kVt, it means that we are decreasing the load resistance, because the gamma by kVt is equivalent to the internal resistance of this NQDS device, while this load resistance. So whenever there is a matching of this external load resistance and this internal load resistance, which is due to this gamma by kVt, then the power output is maximum. So as we decrease this uh, gamma by kBt, it means that the internal load resistance of this NQDS NQDN device is very high. So it needs a large load resistance. So this black one, which is of the order of 5 kilo ohm, it corresponds to the very small gamma by kBt. So one can also like see further details in these publications. Okay, now what happens if we connect a superconductor instead of a normal metal? So we have now like a normal metal, a quantum dot, and superconductor. So it's an N2DS device. So in this N2DS device, one can have various phenomena such as this proximity effect, where the superconducting order leaks into the quantum dot, and the second one is something called the Andrew reflection, where the electron incident towards the normal metal is reflected back as a whole, and a Cooper pair is created in this uh, superconductor. So this is a very important mechanism to carry this uh, current states within this superconducting gap where there is no quasi-particle states. And also the electronic correlation plays an important role in this uh, systems, such as this finite U leads to this something called singlet doublet transition or zero pi transition, and the finite magnetic impurity at the quantum dot can can form a singlet with the electrons on the Fermi levels of this normal metal, which leads to this Kondo effect, which enhance the conductivity large. So the quantum charge transport in these superconductor based devices has been extensively studied in last 2 decades, which leads to various applications such as this nanosquids, Cooper pair splitters, and device for creation and manipulation of these mineral fermions. However, their thermoelectric transport properties are uh, attracting the interest very recently. So these are very recent publications in these fields where thermoelectric transport properties in these superconductor-based hybrid devices has been studied. So the first one is this thermoelectric current in this Cooper pair splitter, and second one is this hybrid NQDS or cross thermoelectric effect in this NQDS device. So this one is our recent publication where we have studied thermoelectric transport properties in NQDS systems. Okay, so in that paper, we studied uh, the N2DS device as an heat engine. So when there is a thermal biasing between these two reservoirs, and also we studied the heat transport Joule heating in this N2DS device. So I'm not going to discuss this Joule heating or this all things here. I'm just going to study this N2DS. Just going to describe this NQDS device as an particle exchange heat engine. So first we uh, studied it using this Hubbard one approximation, and then we extend it to a U infinite limit, which I said that this is a more practical limit to study these strongly correlated materials. So the theoretical formalism remains same as for NQDN device. So we have a something called this Hamiltonian in second quantization formula, which is a effective Hamiltonian. So we have used this Bogolov transformation to diagonalize this Hamiltonian, and then one can calculate the gain functions. So as I told previously that in case of superconductors, the off diagonal part is zero because there is superconducting correlation on the quantum dot. So here we have like all the elements of this 2 by 2 matrix. So this diagonal one is electrons with the spin up and holes with the spin down, while this off diagonal term are superconducting correlations, which is non-zero in case of superconductor. However, the other formalism remains same as for NQDN system. So we have calculated same kind of like current, heat current, power output, efficiency, everything. So here I have shown the linear transport properties of this NQDS device. So here we have like a hot reservoir, which is a normal metal, and a cold reservoir, which is a superconductor, and a quantum dot is attached to these devices. So we can vary like this gate voltage. By varying this gate voltage, one can tune this energy level of quantum dots. So these are schematic diagram for these circuits, this device. So we have seen that this Andrew tunneling only shows the large electrical conductance and no contribution to this thermopower and thermal conductance in the linear response regime. And the reason is that because this Andrew states are particular symmetric states. So the thermopower or the figure of merit cancels each other out, and one can also when we zoom along the y-axis, then one can see these small peaks which corresponds to the quasi-particles outside the superconducting energy gap, and it is seen that these quasi-particle states, due to this diverging density of state, it creates a large figure of merit or thermopower as compared to this NQDN device. So quasi-particle tunneling near the superconducting gap dominates the thermal transport properties, and as I told previously, that the enhancement of this figure of merit is due to this quantum confinement effect or violation of Weidmann-French law. Okay, now uh, we use this infinite limit to study the same system and 2DS system and calculated this power output and this efficiency. Uh, Initially, we optimize it with respect to the quantum dot energy levels. So we find that the value of optimal load varies from like 1 mega ohm to 100 mega ohms, which is different from this NPDN device where the R remains close to 1 mega ohm. But in superconductor, it can vary in a large range as the varies deep. And the efficiency can reach up to 80% of Carnot efficiency while maintaining a finite power output of the order of 2 femtowatt. And now we predicted experimental setup, so one can actually see this kind of results if one consider this lead based superconducting drain reservoir, which has a superconducting energy gap of 1 MeV, and we estimate that the optimal performance can be achieved at a background temperature of 2.3 Kelvin and with a thermal gradient of 1.16 Kelvin. Okay, now let me conclude the work. Our analysis provides an initial steps towards the full characterization of these heat transport and thermodynamic properties in hybrid superconductor quantum group based devices. So this is a very new field, the quantum thermodynamics. So it is only recently people are like studying this kind of system because now it is experimentally possible to fabricate this kind of devices. So the key results from our work are that the green function equation of motion technique, which is computationally inexpensive and straightforward analytical methods, give a reliable results in the Coulomb bucket regime. So we have checked our technique for NQDS system and reproduces the experimental results. Then we extend it to a case of superconductor. So one can see that it's agrees with the experiment quite well. And further, for practical application, it is essential to understand the relationship between power output and efficiency in the presence of this load resistance. So both the power output and efficiency, they peaked for different load resistance. That there is a trade-off between these two, and one can like adjust the load resistance such that one can have a best performance in practical devices. And further, the NQDS system exhibit a large thermoelectric efficiency at finite power output. So we have an efficiency close to the 80% of Carnot efficiency with an power output ranging from zero point 0.5 to 2 femtowatt, and thus this makes it a promising candidate for low temperature energy harvester for quantum technologies and quantum circuits. So these systems can also be this hybrid system also demonstrates some other properties which I have not discussed here, such as this uh, called discharge current, spring current, and heat current based diodes, refrigerators, thermometries, and also cross thermoelectric effect. So these are the references where one can find out these other properties of this NQDS device. And further, one can extend this work to a more complex configuration where one can have more than one reservoir, more than two reservoirs, or one can have a multiple quantum dots, or one can have a multiple level quantum dots, or one can also include the phonon conductivity, which is quite low at this temperature which we considered in this study. So uh, here I stops. So I hope that you find something interesting out of it. So thanks for your attention.
Okay, thank you for
Hello.
your presentation. So
Yeah.
maybe I will ask the audience about questions.
Okay.
So maybe I will have first question. All right. So
Yeah.
so did you look for a experimental confirmation of your results? So there were any what were attempts to confirm your results?
Okay. Okay. So the first, as I told, that there is few experiments in these fields. So the first one is this experiment by Josephson. This one, Josephson and his group. So
But it's a very close name to Josephson, right? But that's not a Josephson,
it's
right?
not Josephson, it's Josephson. It's
Yeah,
here.
yeah. It's all,
Yeah.
it's quite
So
funny.
yeah.
It's
So they have fabricated this device and QDS device. So they have studied both the Coulomb blockade regime, which we have theoretically studied, as well as the Kondo regime. So these are, I think, there are only two experiments which studies thermoelectric transport properties in these devices. But their studies is limited to this N2DN when both source and drain are normal metal. So we have first reproduces their results. So these are the experimental results. You can see here, these are the experimental results by the same group, and these are our theoretical results. But we have one extra plot, but although they agrees quite well, then we extended it to the a system and 2DS system. So in my knowledge, there is no experiment uh, 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 until today which studies these N2DS systems. But yeah, we have like a verified results for this N2DS systems, N2DN system.
Yeah. So what was the temperature of this Josephson nature nanotechnology experiment?
Okay, so yeah, so that experiment works at very low temperature, which is like of the order of 2 or 3 kelvins. So you can see even if when both the source and drain are normal metallic, when both source and drain are normal metallic, so the temperature is of the order of 2 Kelvin. So you can also include a superconductivity because superconductivity also works at the temperature. So we can also like replace the reservoirs with superconductors. So it further enhances the results. It gives the new risk physics because in superconductor there is a different kind of physics as compared to normal metals. So although in both cases the temperature is same even for normal metals because they are also in experimental they have considered the single level quantum dots. So it's possible to fabricate these single level quantum dots when the temperature is very low. So yeah, it works at the temperature of the order of 1, 2, or 3 kelvins.
All right. There is a question from Mr. Stephen Watson. Please go ahead.
Thanks, Christoph. This is
Yeah.
not my area of
Okay.
research, but I'm intrigued by the coupling of thermodynamics and quantum mechanics. That's why I've jumped in.
Yeah.
And so
Yeah.
my question relates to is if I've understood correctly, and again, I may have missed a few things, but you're deriving essentially constitutive laws for fluxes as a function of temperature and say voltage, applied voltage, things of that continuum
Yeah.
nature.
Yeah.
And one of my interest is the question of hydrodynamic models associated with these. So not the equilibrium state, so to speak, the steady state, but let's say the approach to. So are there hydrodynamic limits that you consider to that are relevant in this non-equilibrium setting?
Okay, so we have used this something called this Kildias formalism for to study
Mm-hmm.
this non-equilibrium transport properties. So it is like a well-defined technique to study such kind of systems. But yeah, I don't know whether we have limit or not in that case. But uh, yeah, the technique, this Keldia's formalism works quite well for this kind of systems, for non-equilibrium systems. So, but it depends on the like on your approximations, whether you are using this
Is
Hartree-Fock
there
field or
anywhere you would recommend looking in the literature or in textbooks if someone was interested in hydrodynamic questions in this direction?
I will think about it. But yeah, I think I have not found any reference regarding this all kind of things in my field here. But people have only using that Keldia's technique to study these systems. But
Mhm.
as far as I know, that I have not
Well, maybe I
found
could
any.
ask. So, on an experimental side, if I could just one, this may again maybe outside the scope of what you do, but if you
Yeah,
think of these equilibrium states that they are, you're calling them non-equilibrium transport, but they're equilibrium states that you're either empirically
yeah,
observing or
yeah.
experimentally. Uh, what are the timescales for relaxation into these steady states?
Okay, it's very low. But actually, non-equilibrium by means non-equilibrium, I mean there is a small temperature biasing or thermal biasing between these two reservoirs.
Mhm.
So the current which is due to this, you can say thermal biasing or voltage biasing, it is not time dependent. It is
Well, yeah, but I
steady
mean,
state.
if you imagine a sudden transition, so you're in one
Yeah,
state, and then you say change the voltage in a
yeah.
stepwise fashion, or change the uh, applied jump in the temperature in a
Yeah.
stepwise fashion, how quickly do these systems relax to the new steady state?
Oh, yeah, it's very low. I don't know whether they have considered in the experiment, but in theoretical formalism, we have like simply we consider a voltage biasing, a constant voltage biasing. So
Mhm.
the current which is due to this voltage biasing or the charge current is constant. It doesn't depend on time. It's steady
Mhm.
state. But yeah, one can also include that time dependent part or that
Because it's that
you
time
can say.
dependent part that I'm thinking of when I think of the hydrodynamic limit, some modeling of those transition processes.
Okay, so one can also like include it, but yeah, in my theoretical formalism, there's like no mention of this. You can
Mhm.
say this limit, this time
Well,
limit.
if you think of any great references in that direction, pass them on to
Yeah,
Christian, and I'll
yeah,
try
yeah.
and
Oh,
them.
definitely, definitely. I think there are that Keldia's formalism, the technique. They have probably, I think they have mentioned that kind of time scale or that kind of things, but I am not aware of uh, that kind of things.
Thank you.
I definitely once I become aware of that all thing, I will pass it to Christopher. Chris. Yeah. Actually I'm new in this field. I started this work 3 years back, so I'm still doing like PhD. So I'm layman myself. I'm not an expert, but yeah,
We're,
I will
we're
try
all
to
laymen
like
in science.
yeah. So it's a very rich physics or rich area. So I'm continuously learning this area. So I will yeah. Yeah.
Very exciting. Thank you.
Thank you very much.
All right. So do we have more questions from the audience? Maybe if I will have one more question.
Yeah.
So, so the system under your consideration, you are using Hubbard model. So
Yeah.
can you go to
Anderson,
this to the scheme
it's
of
called
the
and
structure?
this
All
one.
right. Yeah. So this Hubbard model. So you
It's
are
it's
basically
it's it's called Anderson impurity model. Hubbard model, yeah, you can call it Hubbard model, but in Hubbard model, it is for a lattice. It's a single impurity Anderson model.
all right. But I mean the central assumption is this third Hamiltonian, quantum dot Hamiltonian. So
Yeah,
you have like kinetic term. The first is
yeah.
and
The first term is the kinetic term for
and
normal metallic.
and second one is pretty much repulsion term, right? I mean, well, depends
Yeah,
how.
it's just the level energy of quantum dot plus the Coulomb repulsion between these electrons on the quantum dot.
Yeah. So my my feeling is that this model is somehow neglecting kind of more detailed features of a quantum dot, right? So it does assume that quantum dot is a point
Yeah,
like object.
yeah,
Yeah. So I will have a little bit more provocative question. So how the
yeah.
situation would change if you if you start to deform your quantum dot. So if your quantum dot is no longer so much
Huh.
point-like particle, then
Yeah.
probably this picture at some point would collapse or needs to be extended. So
Yeah, it's completely collapsed, because as I told you that these all these results are valid when we have a single level quantum dots. So we have a ideal single level quantum dots. We have an ideal quantum dot which has just only a one energy level. Even if you consider the multiple energy levels of these quantum dots, the all these properties or thermoelectric properties, they will reduce, because then there is no longer a sharp energy level, which is which is the must for these thermoelectric properties. And even if you consider that a multiple level quantum dot, then you have to also consider the phonon contribution of thermal conductance, and that will also reduce that properties. So yeah, for a distorted quantum dot, for a multi-level quantum dot, these properties are no longer there. It's only for a single level ideal quantum dot. But yeah, experimentally you can fabricate this kind of device. Experimentally you can reach to a certain position where you can fabricate this single level quantum dot by uh, excluding other energy levels.
yeah, but let's say if it's not point-like object, probably you have to consider wave functions, right?
Yeah.
Many
Actually,
particle wave functions.
yeah. Actually, this pictures, the second quantization works for, you can say, for it works for strongly correlated materials. It works for also for this, no. But yeah, it was initially used for strongly correlated materials, which you can in which there is a strong interactions, whether it is Coulomb repulsion or other interaction. So yeah, for a distorted quantum dot, the term is more complex as compared to the simple term, which is just single quantum dot energy level and Coulomb repulsion.
Yeah, so
Then you can have a summation over energies of this quantum dot energy level instead of spin.
yeah, yeah, because I'm asking that because I by myself I work on a few of single electron devices
Yeah,
that is implementable in a quantum dots that so under certain constraints you can consider field effect transistor with source and drain as a kind of to quantum
yeah,
dot system, but
yeah.
this is actually not so exactly. So that's why
No, no.
I'm just kind of
Yeah,
wondering
this
which.
is a yeah. This is a completely, like, you can say, ideal experiment, or
Yeah, yeah,
uh, only few labs with high tech facilities can fabricate such kind of devices. So yeah,
yeah, yeah.
but there are experiments on these devices. But you can start from here. Then you can make it a more complex, or you can include the, like, more complex physics in that kind of that model.
Yeah, yeah, I understand. Okay, so just to make a summary. So in your
Yeah,
presentation, so left system, you have two reservoirs. Left
yeah.
reservoir is a superconductor or non-superconductor,
So we have two systems. So in first one, both the left and right are normal metallic. In first one, so the
and the
experiment,
middle. Okay. So there's case one. Left side
yeah,
is
this case one,
normal metal, and right side is normal metal, and the
yeah,
middle quantum dot is metal or normal metal or superconductor.
it's semiconductor quantum dot. Yeah, you can fabricate it by semiconductor or by a normal metal, as long as it has a single energy level. So it
Yeah,
is
but
a semiconductor.
I'm asking.
Indium arsenide. Indium
Uh-huh,
arsenide. Yeah,
uh-huh. I'm
it's a
asking.
indium arsenide.
Okay,
Yeah,
so I'm asking just to inspect the all results obtained by you. So the case one, normal metal,
uh-huh.
semiconductor, quantum dot, normal metal, right?
Yeah. This is case one. Yeah, the simple one.
Okay, the case two. What was the case two?
So in case two, we replace this drain by a superconductor. So in
All
this
right,
colder one, this drain is superconductor instead of a normal metal
all
in
right.
second one. So
And
what
and
happened is that in, yeah,
and the quantum dot is superconducting or non-superconducting?
so it depends on how closely it is. placed to the superconductor. I told you that off diagonal parts of this matrix is non-zero, which means that superconductivity is induced on that quantum dot, which is known as proximity effect. So we have
Yeah. I'm
something called,
asking
yeah.
because your Hamiltonian for a quantum dot doesn't has superconducting order parameters, so
No,
probably it's
this is the Hamiltonian for normal metals. For
yeah.
superconductor, let me show you that Hamiltonian.
Yeah.
The Hamiltonian is a bit different. So let me show you. Yeah, so this one is the Hamiltonian for this NQDS systems. So the first term is the kinetic energy of this superconducting reservoir, this tunneling part, and here it comes. This is for normal metal. This is for superconductor, and here it comes the quantum dot energy part. And the superconducting correlation is due to these parts, this type of
Because
parts.
I see Bogulian operators, but
Yeah,
gamma
so we
Bogulian
have
operators.
yeah yeah so we have diagonalized it using this Bogolov transformation, na. So yeah, initially because the Hamiltonian was not diagonalized, so we have used something called Bogolov transformation to diagonalize the Hamiltonian, and then it reduces to effective Hamiltonian. So one can like solve it further to calculate the Green functions. So yeah, in case of a superconductor, one can have a superconductivity induced on the quantum dot. Actually, we studied that properties in our first paper, which I have not discussed here. So the title of that first paper uh, is this called influence of superconductivity on the magnetic moment of quantum purity embedded in BCA superconductor. So in that paper, we have not studied any thermoelectric transport or any like charge transport. We have just studied what is the influence of superconductivity on a magnetic purity, which is a quantum dot, you can say. So we have plotted this phase diagram or magnetic non-magnetic phase diagram. We have studied this proximity effect or Andrew boundary state or Andrew reflection. So in various parameters, but that was in Hartree-Fock approximation. So as I told you, it's very crude approximations. But yeah, it can give you a qualitative picture about the phenomena or about what's going on there. But one need to consider these higher order approximations or higher order perturbation theory to completely understand these systems. But yeah, it can give you an idea in that paper.
Yeah. All right. So there's another question from Dr. Łukasz Stępień. Please go ahead. Hello?
Yes, sir.
No, I'm just waiting for Łukasz Stępień because okay, he was raising the hand. Okay, maybe one more kind of question or possible request. So there was one slide on this green functions technique that you use special.
Yeah, this one.
Not. I mean, this is pretty kind of typical. This no, the before this one. So can you
Okay.
can you elaborate? Can you maybe give deeper meaning of this first equation that is
Okay, so actually what happens is that this first term, written in this double notation, something like this, na, this is called the Joubrev notation of a green function. So what we create a particle at as sir previously asked a question about the time scale. So I don't have any idea about that time scale, but yeah, we initially created a particle at t is equal to 0 time, and then after a certain time we destroyed that particles. So uh, this kind of things are known as the collators or propagators. So the particle propagates through this interacting system. So we created a particle and we destroyed a particle after time t. So within this time interval, the particle interacts with the system. So if the system is like, you can say, if the system is non-interacting, then particle goes without interaction, and the green function is simply 1 upon omega minus ed plus I eta, which is not which is like this is Dirac delta function. So if there is an interaction, it become a Lorentzian kind of function. So this kind of term represents this green function, which gives us the properties. So this green function satisfies a equation. If you solve with this green function, it satisfies equation. This is known as the equation of motion for this green function. So if I solve this equation of motion for uh, this Hamiltonian, then in that equation of motion, one can have higher order Green's functions. So that something like the Green function like this appears in uh, that uh, equation of motion. So one need to calculate that kind of gain function also. So it become a very, like you can say, complicated task to calculate the higher order gain function. So one need to stop at certain point, and which is decided by these approximations. So at the lowest order, so these kind of gain functions can be written like this. So this is something called the mean field approximation. So electrons are interacting by a mean field. So there is no one-to-one interaction between the electrons. The electron is interacting with the mean field of the electrons. So these kind of approximations are simple as the mean field. Then if one need to go beyond that approximation, then one need to write down the equation of motion, this higher order gain function. So can I show you one slide? Means like one paper. So I have this. So here we have like in that paper. Can you see the paper?
Yes,
First slide.
I can see. Yeah, maybe can you open? Do you have some PDF of this paper or on your computer?
Yeah,
or...
I have an PDF. I have an PDF. So I think it's that it will become like easy to, let me.
Yeah, and then after that we have also one question from Dr. Łukasz Stempin, but let us first see
Okay,
this PDF.
okay. So yeah, so now can you share that PDF? Can you see that PDF?
Yes, I can see, right.
Okay, do you hear me? Do you hear me? Hello?
Yes, we can hear you, right.
Okay, fine. Thank you very much for a very interesting talk. I'm not any specialist on quantum dots. However,
Yes.
however, I would like to ask for such issue, namely, as I understand, your quantum dot is one of the versions, yes, of one of a kind of quantum dots, yes. There's
Yeah.
So okay, so one of the interesting applications of quantum dots is building quantum computers.
Yeah.
Yes, and my question is that what are the chances of opportunities of building quantum computer basing of such quantum dots as this one analyzed by you?
Okay, so we have studied these. We have not studied these charge transport properties or spectral properties, which is must for this quantum computer. We have studied the thermoelectric transport properties of these quantum dots. So yeah, one can use, like you can say, if you have a quantum circuit which is used to produce these quantum bits. So in that circuit, one can use the heat energy produced by this circuit to generate the power output in that circuit. One cannot reproduce the qubit from these kind of systems, but yeah, uh, for that one can have like both the reservoirs as a superconductor. So if both the reservoirs are superconductor and a quantum dot is attached to that, then that system can be used as a qubit. But in our case, we have one normal metal and one superconductor which is attached to a quantum dot. So we have studied the charge transfer property, thermal transfer properties in this system. So this can be used to as a miniature power generator in that circuits, quantum circuits, but not to reproduce these qubits.
Okay, thank you very much. Thank you very much for all these explanations.
But one can use this as 2DS, superconductor-based Josephson junction, to reproduce that qubits. We have studied that systems. We are studying that systems. But
yes.
yeah.
Okay,
But
thank you very much.
Thank you, sir. Thank you, sir.
Yes,
okay,
yes.
So, yeah.
So can we come back to this paper, explanation of this paper?
Yeah. So can you see that PDF?
Yeah, but can you go to the very beginning, so just to evaluate us the main assumptions of this approach? Just because your explanations was a bit too quick. So if I can ask you to be more elaborate on this approximation done by you.
Okay, so this is the paper, and now strongly correlated systems of quantum dot heat engines. So can you hear? Can you see this paper?
Yeah.
Okay, this is a paper where we have studied this N2DS system and reproduces these experimental results. So yeah, so these are this schematic diagram of that systems. So we have both source and drain as normal metal, and we have a single level quantum dot. and we have this external circuit. So this load resistance where the power output is seen in across this load resistance. Okay, so we have considered this Hamiltonian, this reservoir, quantum dot, and tunneling part. Where this reservoir, this quantum dot, and this tunneling part.
Yeah, this is so far fully understandable, right? Yeah.
Yeah, you can. Yeah. Then we have used these equations to calculate charge and heat current, and then occupancy, and then the Kildias equation. We even see the Kildias
Yeah. So
formalism.
I see that by this Fermi Dirac distribution functions, you assume that the left and right reservoir is in a sort of thermal equilibrium, at least can be
Yeah,
parameterized by temperature, right?
yeah. They have just a temperature difference. They have a small temperature difference.
Yeah.
But in the linear response regime, one can like do an Taylor series expansion. But since we are interested in the non-linear regime, so we have just used these formulas. Or you can see the definition of green function here. Can you see this one, the part which I highlighted?
Yes,
This
I
one.
can see, right. Yeah.
So this is the green function of this direct green function.
Yeah,
So you can
it's
see that we have,
standard green function. Yeah.
yeah, it's a standard green function. So you created a particle at time t dash and you destroyed it at later time t.
Yeah.
So what particle did during that time period is captured in that green function. If it interacts with, then the green function is Lorentzian. If it goes without interacting, then the green function is Dirac delta, non-interacting particles. So we have calculated the green function. So this green function satisfies an equation which is known as the equation of motion. So let me show you that equation. In appendix, I've written that equations. This is the equation. So can you see that equation?
Yeah.
It's
So
A1.
actually, this equation was a part of the question. So
Yeah.
you have these two types of brackets: double bracket and single
Yeah.
bracket. Yeah.
Yeah. The double bracket is known as this Jubrev notation. So this
Okay.
double bracket, the anything which comes inside the double bracket is Green's function. And this one is the average over ground state energy. So this one is the average and this one is the Green's function.
All right. I see. Okay.
So you can you can write down this equation of motion for any green function. So you have to use this something called this Heisenberg equation of motion. I think you are familiar with them in
Yeah.
quantum mechanics.
Sure.
So any operator satisfies these equations that you can say. So you for green function you can derive this equation for any green function. So we started from these green functions, and once uh, we have to calculate this something called this commutator brackets. Can you
Yeah.
see this commutator bracket? This
Yeah.
D and
Sure.
H.
Yeah.
So where one can calculate this commutator brackets, and then one can have this higher order gain function, which I showed you in the slide D and D diagram. This is a higher order gain function. And then if if one is like directly taking this L sigma out of this Green's function, which is known as the mean field decoupling. So there is like you can say there is a Feynman diagram which correspond to this kind of decoupling schemes. So I have
Okay. I
not
see.
shown here it. So there is a Feynman diagram. So there is a processes, the lowest order processes in which you can take this N sigma out of this Green's function. So and you can put it here, and you no longer have a like you have only a this kind of green function. You don't need to worry about this kind of green function because it is written like this, and you can have this kind of greens function which is a simple mean field green function. Is it
I see.
clear?
Yeah.
then 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 for higher order approximations we have to calculate the green function of these higher order functions also. So here I have shown this kind of green function for these higher order functions. And then this higher order gain function also contains several other gain functions. This is much higher than that. So one need to use another approximation known as Hubbard one approximation. So these all things are clearly mentioned in that papers. So that there is a paper of this 85 reference, this Hubbard, 1963 paper.
Yeah. I know this paper
Yeah, this is
because
standard paper. Yeah.
yeah.
So each and every decoupling scheme is clearly mentioned in that paper, and then we have calculated this Green's function, and then one can have this more higher order of equations. Then one can calculate the Green functions. So these are, so the basic idea is that this gain function satisfies an equations, and we have to solve that equations by using various approximations, because the equation is not coupled equations. Because if interaction is there, then the equation is, we have we have an infinite set of equations. So we have to like convert that infinite set of equations to a coupled equations by using this approximation. We have to stop that uh, infinite array of equations by using the approximations. Are you getting my point? But yeah,
Yeah, I got your message. Thanks for a long answer, and thanks for yeah. So do we have any more questions from the audience? Okay. In such case, I will thank you, the speaker, again, and let us be in touch. And great thanks for this nice seminar. So let us keep touch to move on with our ideas.
yeah. I would like to thanks you and the audience for this wonderful opportunity. And yeah, we will in touch.
Okay.
Yeah,
So thank you, guys.
yeah.
Thank you. Bye
Thank
bye.
you. Thank you. Bye bye. Thank you, sir.